So this is part 2 of our lecture on chaos. And just a quick refresher, remember we have this bifurcation diagram for values of R ranging up from 2.4 up to 4. You get a single value up to R equal 3, and then we get two values. That's found by drawing a vertical line here, two different values up to 3.45, and then we get 4 values and 8 values. So now what I'd like to do is first refresh on a couple of different ways to present these results. Here's the logistics curve and a diagonal line. Starting at this point, about 0.3, we find that for a value of R equal 3.2, for a value of somewhere around 3.5, we would end up with 4 values. That's one way to depict this. Here's a second way, using a spreadsheet and repeating the result, iterating, and you can see it very quickly settles into 2 values for R equals 3.2. The next and probably most important way to present the results is the bifurcation diagram. So at this point, I'd like to show you an animation of what happens if we zoom in on particular areas, like this bifurcation area here, or even this strip that appears to be empty. That's the white space, which has a little smudge there. We're going to look at that. So bear with me. We're going to, well, I guess first we will show an animation of this style. So this is a little movie that I prepared or found and copied. So you'll see the person operating this is choosing different starting points. And you can see for this fairly low level, that was a low level of R. Now we have R equal 1.37. And we see no matter where we start, we end up at the intersection of the curve and the line. So they're just clicking on different choices. Now we're at 2.15. And you see, once again, we migrate to the intersection point right there. It doesn't matter where you start. That's illustrated by the way the person is operating it. Now we're going to get interesting. 285 still has that same behavior, except now we go into an orbit around the intersection point. No matter where we start, we end up right here. Actually, if you look close, there's a little red dot showing where we finish. Now things get interesting. 3.2, and we start, and we get an orbit, 2 values of population. And now they're iterating to show you how this progresses. It's similar to what I showed earlier. Around it goes, and eventually it stops changing. And you see that the population oscillates between this value and that value. Now we're getting crazy high, and we have chaos. So no matter where we start, we get some kind of chaotic behavior. It's not the same now for this. It's not the same. So starting at different points and iterating, you see the population oscillates all over the place. It never actually closes, never stops. Okay, and we'll just let this run to the end. Okay. Now we're going to look at this bifurcation diagram animation. So let me drag this in. So you can see the similarity between these. So this one, we're going to use one of the online tools where you just select an interesting area and it zooms in. And you have to refresh each time. So in here, we're looking at a spot where we're going to get 8 values. But we also see chaotic behavior here. And keep note of the values from here to here for R. So if you zoom in on that white area, you're actually looking here to here. The values of R are not ranging very far. And here's that echo I talked about. In fact, if we zoom into the white space in the echo, we see, I know there's a lot of cursors, but we see the echo again. And if we zoom into that one, has a white space and it has an echo. And that one has a white space. And notice at by this point, there's almost no difference between the starting and ending values of R. We're just completely zoomed in, studying microscopic detail in this bifurcation diagram. Still getting echoes. And within every echo, there's a echo. And now you see we're getting kind of rough looking results because the computer's mathematical precision has been exhausted. So those are two interesting animations of how these things progress. So we've done that, and we saw this. This is the model we just looked at. Here's a link you could follow if you want to download one of these tools. Take note of this warning here. Whoops. That most of these models or these mathematical tools are built in Java. And Java has some vulnerabilities that you have to be aware of. Most browsers will challenge you and say, please don't use Java in this way because you could be vulnerable to hacking. But you can dictate to the browser that you're willing to use only a JavaScript from a particular source. And in this case, it would be this source here from a university in Japan. And that will give you some protection. And when you're done experimenting, you can set your browser back to not accept any Java of this type. Okay, so now we're on to the second part of the presentation. I should go over this. So we're going to look at animations of different kinds. We're going to introduce Mitch Feigenbaum, one of the pioneers in doing this kind of work, and the concept of universality. So here we go. So chaos was known to mathematicians. Poincaré, a French mathematician, knew about the foundations of this theory back in the 1890s, but did not have a computer to generate either the numerical results or the graphical results. In the early 1960s, computers became capable and available, and things changed. So there's a reference to Poincaré. Ed Lorenz has already been mentioned in video number 1. He was interested in the limits of weather prediction, influenced by the limits in the quality of measurements that could be made. And he did use computers to illustrate these results to colleagues and generate interesting new results. Here's a reference to something you might have heard of, the butterfly effect. There's actually 2 versions of this, but it was Lorenz's idea that a butterfly flapping its wings in Brazil could cause small-scale disturbances in the atmosphere that might propagate, ultimately leading to a completely unpredictable event like a hurricane or a tornado. This note here is actually a note to me to add more detail to that. But you can look this up, the butterfly effect of Ed Lorenz. There's a lot of different current applications for chaos theory. Here's a list, certainly of mathematical interest, but it has applications in physics. Something we'll talk about later is the concept of fractals and their relation to the measure of something such as the coastline of an island, where the measured coastline depends on the scale of the ruler you use. If you use a 3,000 kilometer ruler and go around Australia, you'll get quite a different number than if you use a 3 millimeter ruler. We'll talk about that some more. Social and population systems are areas where chaos theory has been applied. Biology, we've already talked about population dynamics. And meteorology is one of the areas where Ed Lorenz's work provided pioneering insight into what goes on in weather systems. So this is a list of areas where chaos theory might be applied. So we've been talking about the logistics function, and it's an idealized function. It relates population to the rate of change of population or the increment of population. But real populations are not a smooth parabola like we've been talking about. They might have some shape like this. Something to keep in mind for a topic we are going to discuss that relates to what is called universality. Okay, and there's some language here that we've already covered that illustrates why a curve would look like this. As the population grows, its ability to grow from that point is limited by factors like aging, limitations in food or water, arrival of predators, and various other things. And to make the model manageable, we've replaced this kind of complicated model with a parabola, such as the one that just came on the screen. So let's look at how the population grows in time from a logistics function. So here is population growth as a function of time, and this repeats, so we'll talk about this for a second. A small population grows, it has a period of high growth rate, and then ultimately you get to a situation where the population is limited by resources, predators, disease, and so forth. And so these little red numbers could represent how many rabbits we have in the field that we talked about earlier. Now, if we have the same field and the same behavior of the rabbits, when we introduce predator, now here rabbits are now switched to being blue. We have foxes. We've introduced foxes, and their population grows, but will stop growing when they've exhausted all the food supply, which is illustrated by the blue curve now, where the rabbit population crashes because there are so many foxes that they've killed all the breeding rabbits. So this is the kind of behavior you'd expect. Population as a function of time if you have exploiting the logistics function, and in this case over here introducing multiple species, one of which is a predator, one of which is a prey. Now let's go back to our bifurcation diagram, and here what we're doing is we're watching the R factor right here creeping across here. Imagine a vertical line. Here we're at 2.8 coming up right here. So we're here. We're still getting one value, but as we get close to 3, now we have 2 values. We have an upper value and a lower value. That's occurring in this regime. As R continues to get bigger, now we have 4 values. 1, 2, 3, 4. I wasn't quick enough to show them, but we'll show this again. And then we have this chaotic period. So let's let it run through. So it's starting over. So here we have essentially time, and as R grows, the population grows slowly. That's this regime here. Then we have a transition to a bifurcation right here. R equals 3, we start getting 2 values, 1, 2. At 3.45, which is coming right up, we're going to have 4 values. Here they are, 1, 2, 3, and 4. Then we get something like chaos, and now watch, we get a period of quiet right now. That's this slit right here, where there's only 2 values in the slit, right? There's 1 value there, one value there with some slight complication by that echo we've been talking about, which is in this part of the gap. So let's let this run one more time. Once again, the R value is here, and we're working our way across. Imagine a vertical line intersecting the curve. So we're here, now we're here. We're getting close to this. Right there we have, whoops, we have 4 values, and we have many values. And watch again as we get a quiet right there, where we only have 2 values. Okay, sorry I interrupted that. So let's look at this in slow motion. Now here's R equal 2.8. This is an analog for time. So the population grows and stabilizes. Here's a higher value for R, 3.3, and the population grows and it stabilizes, but it oscillates between 2 levels. So we've passed through the bifurcation point at 3.0. Here at 3.5, we have 4 values, 1, 2, 3, and 4. And then we have chaos, where in this case R is 3.8 something. And then we have period of stability, that is, there's 2 levels. And then we have chaos right in here, completely unpredictable. And then things settle down, and we're back to 2 values again. That's this particular case, we go back, represents this gap right in there. So let's go through these again. So by now we've gone over this quite a few times. I think it should be clear to you what's going on here. We're in this gap, and it's predictability that goes right out the window when we have an R value that big.